Dear students, welcome to this seventh session of our chapter 4 Chemical Bonding and Molecular Structure. In the last class, we have started the topic hybridization. What is hybridization? It is the intermixing of two or more atomic orbitals of equivalent energy to give newly formed hybrid orbitals, or the equivalent energy and shape will be there for the newly formed hybrid orbitals. And we have seen the sp hybridization and sp2 hybridization. Now in this session we'll start with the sp3 hybridization. By the name itself we can understand that which all orbitals are involved in the hybridization. One s orbital one s orbital and three p orbitals, giving how many sp3 hybrid orbitals? 4 sp3 hybrid orbitals. And this can be explained by the methane molecule, where the mixing is between the 1s and 3p orbitals to give the equivalent energy and shaped hybrid orbitals. And we can understand that in this sp3 hybridization, it's 25% s character and 75% p character in each hybrid orbital. And the four sp3 hybrid orbitals which is formed are directed towards the four corners of the tetrahedron, which is having an angle of 109.5 degree. So this is about tetrahedral shape, the molecule which possesses. Now we can see the carbon's ground state in methane. It's having 1s2, 2s2, 2p2. And here we can understand that outermost shell 2 unpaired electron is there. If the carbon is in excited state, the one electron from 2s has to be promoted to the vacant p orbital. So what happens? The configuration becomes 2s1, 2p3. 1s2 is not at all moved because it is the inner shell. Now we are having how many unpaired electrons? 4 unpaired electrons are there. And as we know that in methane, 4 hydrogen atoms are there with 1 carbon. So each unpaired place is occupied with the opposite spin of hydrogen. That means there will be hybrid overlapping of s orbital of hydrogen with the sp3 hybrid orbital of carbon. That means we are having here 4 sp3 hybrid orbitals, and each hybrid orbital is overlapping with one s orbital, giving us sigma bond. So the structure we know that in methane is carbon at the center having a sp3 s overlap giving a sigma bond. That means CH4 bonds are there. So this is the structure of methane molecule where we can explain the sp3 hybridization. Let's see the hybridization in ammonia molecule, which is also taken as the example for sp3 hybridization. In ammonia molecule, we know that the nitrogen is the center atom and the terminal atoms are hydrogen. So the center atom's outermost electronic configuration first we'll see. So what is the atomic number? Nitrogen is having 7. So 1s2, 2s2, 2p3. Then outermost electrons will be 2s2 and 2p3. So looking at the configuration, we can understand that how many unpaired electrons are there. In 2p, 3 electrons are there. That means it is unpaired. Okay. Then how many 2s electrons are there? Here it is paired. So we are having how many sp3 orbitals? We will be having here 3 sp3 hybrid orbitals. But one is what? One is the lone electron, right? So we will use the 3 sp3 hybrid orbitals for the overlapping of hydrogen atom. That is, s orbital of hydrogen will overlap with the 3 sp3 hybrid orbital. And one is what? The lone pair. The fourth one is the lone pair. So what happens is 3 NH sigma bonds we will get. Since the force of repulsion between a lone pair and a bone pair is more than the force of repulsion between the two bone pair of electrons, we know this thing. because we have learned that lone pair is having more compared to lone pair compared to bone pair of electrons. The molecule thus gets what? Distorted, and the bond angle is reduced to 107 from 109.5, because 109 was the 9.5 was for the tetrahedral geometry, and because of the lone pair here in ammonia molecule, the molecule's geometry is getting distorted, and it is reduced to 107 angle between the bonds. So the geometry of such a molecule will be pyramidal in shape. It's not tetrahedral, it's pyramidal in shape. Now you can see the nitrogen here, 2s2 and 2p3 is there. So how many electrons are there? We know that 3 is unpaired. That 3 is used with the s orbital of hydrogen atom for the bond formation. The 2s electron is here without bond formation. That means it will be acting as the lone pair. So when we make the structure also, 3 NH bonds are there with a lone pair of electron. Due to this lone pair, what happens? The tetrahedral geometry is getting distorted. So the angle between the NH bonds, that is, it becomes what? 107 degree. Otherwise, it should be 109.5 degree. The next example is water molecule. And in this water molecule also we can see the sp3 hybridization. So let's see how it is. So central atom is oxygen and atomic number of oxygen is 8. So we'll write the electronic configuration 1s2, 2s2, 2p4. And we can understand with that outermost shell that there is only 2 unpaired electrons. So when the hybridization is done between the s and the p orbitals, we will get 4 sp3 hybrid orbitals, out of which 2 will be having 1 electron each, and the other 2 will be having a pair of electrons. Right? Now, these 4 sp3 hybrid orbitals acquire a tetrahedral geometry with two corners occupied by hydrogen atom, while the other two by the lone pairs. How it is occupying? Because the two unpaired electron in the p orbital will overlap with the hydrogen atom's s orbital. That means sp3 s overlap is there. So it gives you a sigma bond, and that's why we are saying that on the tetrahedral geometry, two corners, these two hydrogen atoms will occupy. And what about the other two places? The lone pair is there. So the bond angle in this case is reduced from this 109.5 to what? 104.5 degree. As and the molecule acquires a V shape or the angular geometry for water molecule. And this happens, the reduction of bond angle is due to the lone pair of electrons. There is two lone pair of electrons. That's why the geometry is getting distorted. We can explain the hybridization in the orbital diagram like this. That is, the 2s orbital is having 2 electrons. 2p is having 4 electrons. And in one of the 2p subshell, 2 electrons are there where the other two are unpaired electrons. Right? Now, these orbitals will intermix. So, how many hybrid orbitals will get? 1s and 3p orbitals will intermix to give what? sp3 hybrid orbitals, right? Now, what happens is when these 4 sp3 hybrid orbitals are there, we are having only 2 hydrogen atoms. So, the 1s orbital of hydrogen atom will overlap with the unpaired electron of 2p orbitals. So, making it what? Making it a sigma bond of sp3s hybridization. And the remaining 2 will be what? Lone pair of electrons. Lone pair of electrons are there in the two subshells. So these, when it is placed in a tetrahedral geometry, two places are occupied by the hydrogen atom corner, and the other two will be having the lone pair of electron. So there will be lone pair repulsion. Due to this lone pair repulsion, what happens? The geometry of tetrahedral is getting reduced to 104.5 degree with the angle. So it will acquire a V shape or angular geometry for water molecule. So this is how the sp3 hybridization is explained. Now let's see the next type of hybridization, that is sp3d hybridization, and it is explained with the example of PCl5, phosphorus pentachloride. In this itself, we can understand that one s, 3p, and one d orbitals involvement is there in the hybridization. So it can be said that it will give you 5 hybrid orbitals, right? And this type of molecule is having a geometry of trigonal bipyramidal. Trigonal bipyramidal. In PCl5, if we are seeing this example, we can understand that phosphorus is the central atom. Phosphorus atomic number is 15 and chlorine is having 17 atomic number. Now, the three chlorine atoms lie in one plane, making an angle of 120 degrees with one another. And these atoms are called equatorial atoms. And the bonds formed by them are called equatorial bonds. What about the remaining two chlorine? The remaining two chlorine lie at right angles to the plane of equatorial bonds and are said to be axial atoms, and the bonds formed from them are called axial bonds. That means in PCl5 we are having two types of bonds, axial bonds and equatorial bonds. So center atom is phosphorus and it will make 5 bonds with chlorine. Axial bone pairs suffer more repulsion from the equatorial bone pairs. Therefore, axial bones are slightly longer and hence weaker than the equatorial bones. This point you have to keep in mind. While you are drawing the structure, keep in mind that the axial bones are slightly longer and they are weak compared to the equatorial bones. Phosphorus atomic number is 15. So we'll write the configuration 1s2, 2s2, 2p6, 3s2, 3p3. The ground state outer configuration will be 3s2, 3p3. Now with this we can understand that here 3 unpaired electron is there, right? And we are having here how many chlorine atoms? We are having 5 chlorine atoms. So each chlorine's p orbital, because chlorine's atomic number is 17, and when we write the valence electron it will be 3s2, 3p5. 3p5. So the one p orbital is having unpaired electron which has to overlap with the phosphorus unpaired electron orbital. So each chlorine will be hybridizing with the phosphorus empty half filled orbital, not empty, half filled orbital. So how many unpaired electrons we should get in the phosphorus? 5. For that we don't have that much, we have only 3 here. So what we can do is we can excite the phosphorus and the 3s electron has to be promoted. But when we are having only 3p orbital here, where we will shift, wherever you will shift it will become double, that is pairing should be there. So it's not possible. So what we can do is we have to take the next higher energy level, that is after 3p it comes 3d. This 3d when we are taking, we'll get here 5 subshells. So the 3s electron has to be promoted to 3d orbital. So when it is going to 3d1, now how many unpaired electron we are having? In 3s1, 3p3 and 3d1. Total 5 unpaired electron orbitals we are getting. So each unpaired electrons when we add up one chlorines, or when these sp3d hybrid orbitals, when it is overlapping with a p orbital, it gives you a sigma bond. That means 5 PCl bonds you are getting in the structure. These 5 structures are sigma bonded because the overlapping is between the sp3d and the p orbital, giving a single bond or a sigma bond. So this is having a shape or the geometry trigonal bipyramid. And these chlorine atoms, this is 1, 2, this one you can take 1, 2, 3. These three chlorines are said to be equatorial bonds or equatorial atoms of chlorine. What about this chlorine and this chlorine? These are the axial chlorines. So these are having little long bonds, and it is weaker than the equatorial bonds. This we have to keep in mind. So this is the shape of a triangle, and above the plane and below the plane one chlorine atoms are there, which makes the geometry triangle bipyramidal. Like up one pyramid is there, down one pyramid is there. So this is having triangle bipyramidal shape. Next one is the sp3d2 hybridization. And here we can understand that six hybrid orbitals are formed. That is 1s, 3p and 2d orbitals. Intermixing is done to give six hybrid orbitals. And the example is with the sulfur hexafluoride. And in sulfur hexafluoride, we know the sulfur is the central atom. It's having the outermost shell 3s2 3p4 because 16 is the atomic number. Now we can see that in s orbital it is paired, p it is 4. That means we are having in this only 2 unpaired electrons, but we are having 6 fluorine. For 6 fluorine to accommodate, we need here how many unpaired electrons in the sulfur? We need 6 unpaired electrons. So we don't have. So what happens? We have to excite the electrons to higher energy level. That is 3d orbital we have to take. So in the excited state, we have to make available the 6 orbitals. That is 1s, 3p and 2d orbitals, where we will get the 6 unpaired electrons in these 6 orbitals. And these orbitals hybridize to form 6 new sp3d2 hybrid orbitals, which are projected towards the 6 corners of a octahedron. So the geometry will be octahedral geometry. And the sp3d2 hybrid orbitals overlap. The 6 sp3d2 hybrid orbitals then overlap with the fluorine atoms half filled p orbital, or they will overlap with the p orbitals, giving 6 sulfur fluorine sigma bonds. Sulfur fluorine sigma bonds with the geometry octahedral. Now you can see the orbital diagram here. That is sulfur in its ground state 3s2 3p4. You can see here only 2 unpaired electron is there. We have here 6 fluorine. So what we can do is we can excite the electron to higher energy level. Why? Because if you are exciting this electron, where it will go? It will go here. Again you will get what? 2 unpaired electron only. So there's no meaning in that one. For that we have to take the next higher energy level, that is D. So when this electron 3s is shifted to the first one in D, what happens? We will get 3s1, 3p4, 3d1. But it's not complete. Why? Because right now we are having only 5 unpaired electrons. So what? Here in the p also we are having the 2 electrons. This one electron also should be shifted to the d orbital, but it can't be in the same shell. So we have to keep in the next subshell. Now we are having the 6 unpaired electrons, 6 shells or orbitals, and this is used up by the fluorine atom to make the bonds. So 6 sulfur fluorine bonds we are getting with the hybridization sp3d2, and it possesses a geometric octahedral geometry. That means you can see here 6 fluorine atoms are there, which is attached to the sulfur atom, but 4 are on the same plane, and in planes above one is there. Above the plane one fluorine is there, and below the plane one fluorine is there, making a square bipyramidal shape. And it possesses a geometry, which one? Octahedral geometry. So these 6 places where the fluorine atoms are there, it is the octahedral corner of this sulfur hexafluoride. Thank you. We'll continue in the next session.